Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the NPTEL course on remote sensing and GIS for rural development. This is week 6, lecture 1. In the past week, we have been looking at multiple data types in GIS, especially raster and vector data. And we have looked at how those could be applied for rural development. It is important to understand that rural development, when it becomes complex issue, there could be multiple data sets that one can download. It need not be a particular type always, right? One time it could be a raster or a vector. So we cannot pick and choose between data set. Usage of data for analysis will determine what type of data we will use. Moving on, we will look into the aspects of data collection and how data is being collected. And then we will use it for our rural development aspect. Let's see what we are going to look at in particular in this week. So in this week, we will finish up one more introduction part that we had in the last week. So in week 5, we looked at raster and types. The most important types were the JPEG, TIFF image, grid image, those kind of things. And we specifically looked into the difference between vectors and rasters. As I again say, which type is correct, anyone can ask, but there's no right or wrong here. It depends. It depends on your work. It depends on your problem statement and the data availability. If you have very good data for river network and water availability, you can definitely use vector data. However, if that data is less and not available, then one has to use raster data and other kind of proxy data. Then we looked into the introduction of raster tools. In continuation of looking at the vector data types, we looked into the raster data types and tools. Then we looked at some examples, especially the masking tool, where we developed an entire data frame and then we extracted based on what is needed for us. Okay, so that was the masking tool. In week 6, what we are going to do is we'll combine both now. So vector plus raster in our analysis. Before that, as and when you download data and when you look into the metadata, two things which are very important are the coordinate reference system and projections. It is important to understand this while downloading raster. So I am continuing with the introduction of GIS with rasters and vector data. But when you bring down raster data from a portal, it is important to understand the projections and coordinate system. This is true for even vectors. So let's look into that in this week. What is coordinate reference system and projections? We will cover this today in this lecture. And then further along the week, we will look at converting from print or image form to raster, which means you could have taken an aerial image from a plane or a drone image. How can you convert it to raster? Similarly, you would have taken a data point from a data source from satellites. How do you convert it to a raster? We will look into that, and that is mostly called georeferencing. We'll give an introduction to georeferencing, and then throughout the week, we will extract information from this georeferenced image. Thereby, I'll be teaching you on creating new point files, line files, and polygon files. These are important files to have for rural development because they don't get updated often. So the rasters get updated often. Why? Satellites, drones, etc. are taking images. But point data gets tricky. One has to develop an updation system to update periodically the data. If you do not update, then there is a big lag. So let's jump into that today. We'll be looking at projections and coordinate system. In an overview, we will look at projections, coordinate system, datums, what is a datum and how it's being created in a projection and coordinate system, examples of different projections, and you will also see some data frames and data sets. Okay, so this will be more discussed when we do the hands-on setup. When I say hands-on, I will also open QGIS and download our data and show you. And in that time, we will look at the data frame and how you can convert the projections, etc. So already we have seen some of it in the previous examples. We will have more clarity when we do more examples later. So moving on, we will look into the panels of projections and coordinate system, description of panels, projections and coordinate system. But before that, we will have to look into what is the location. So we've already looked at location in multiple directions. Today, we will look at this from a map angle. So in an unprojected geographical system, you do not have coordinates. Okay. Let's take a sphere, a globe. It is not projected. It is a real life, real globe. And the earth is kind of modeled in a globe, right? So what we have here is, this is a globe which has been dissected into grids. And this grids is what gives rise to coordinate system, the type of grids and how they, what is the degree between it. So let's take, there is a center. You could see in my pointer shortly that the center is here, and from the center, the entire globe can be gridded and angled, right? So you have angles for each grid. Let's show an example. So this is 0 and this is 0, right? So from 0, you can go vertically up as an angle. So this is latitude lines. The latitude lines are running top to bottom, let's say for the earth, and then running on the horizontal axis is longitude. Okay, so the vertical one or the top to down one is the latitude, whereas the longitude runs along the perimeter and it is in the horizontal direction. So if you take a center, so both have centers, right? So in a vertical also you'll have a center, and a horizontal also you have a center. So let's take from here, and it is the 0, and from the 0 it goes 55 degrees. So that is lat. So every line is being cut. Okay, so the globe is cut into different lines. So like cutting your orange, right? And then longitude is also cut, and that is a particular coordinate system. So every coordinate system has its own way of telling it or describing the the 0 and the coordinate system. So the lat long system measures angles on spherical surfaces. 60 degrees east of, let's take an example, 60 degrees east of prime meridian. The prime meridian is the 0 line, right? So from here you do 60 degrees. So I'm going to describe a location. So the location is from the prime meridian, which is the 0 point. From the 0 point, it is 60 degrees east. So you move 60 degrees east. So you move to this point. Remember, each location should have a lat and a long. It is not a 1D surface where you, or 2D surface where you can just put one point. Even a 2D will have X and Y, right? So here we're trying to show an X and Y. So there are two dimensions, and X is given by the 60 degree east prime meridian and 55 degree north. From this, you go up 55 degrees. So when you go up 55 degrees, the zero is kept here. So that is the line here. And from the 0, you're going up. So this is the central 0, and there is a y-axis 0. Okay. So then you merge this, and from here you calculate what is the angle you want to go. So 55 degrees north of equator. So from here, 55 degrees north. So this point is what we want to look at and represent in our study. So this is given as, the location of this is given as 55 degrees north, which is from the equator, the center, you're going up 55 degrees north, and 60 degrees east is from the prime meridian, you went 60 degrees east. So if you just take one, for example, you take this and then leave it here, you do not know that how do you go up and down, right? So at 60 degrees, you can have 55 up or 55 down, 55 degrees from the center down. So all this is being created when the coordinate system is driven. So when the slices are made, the angles are given, the difference between each slice, there is a particular angle, and that has been taken. Why is this slicing done? We will discuss this when we compare a globe and a real life scenario. Okay, so here is where the datum is, and the datum is the 0 part. So you have equator and then the prime meridian. Okay, so the prime meridian runs from top to bottom, and then the equator runs along the horizontal line, right? So the prime meridian goes to the north and south pole, whereas equator runs along the horizontal part, and you could see that they meet at one point in the center, right? So you have this round, and then in the center they could be along the circumference. When I say meet, virtually, it's not like they actually meet, right? So you can drill down from a 2D surface, they meet. However, the globe is a 3D surface. So this is in the center, whereas you have it here. So along the prime meridian, you start at 0, and then from the 0, you go 60 degrees, and from 60 degrees, you go up 55 degrees. This is the example we have done here. So this location is what we have given as per the 60 degrees east and 55 degrees north. Now, we are going to go to projections. So before that, taking a step back to just show that this is a coordinate system where you have given coordinates to the globe. The globe was a 3D surface. It did not have any cuts. It doesn't still have. It's still a virtual line. And why we do that is we want to represent in a 2D surface, but the globe is a 3D surface. So to cover that, it's the same like you do integration. What you do is you dissect it into small parts, and within the small parts, you can assume it's a 2D, right? And then you add on to it for the entire globe. So just a small part you cut, and that small part location is given as a 2D surface with 2 dimensions, your north and east lat longs. So now we go to projections. Everyone knows the Earth is not a ball, it's not a sphere, it's a spheroid. Okay, which means it is circular but stout on the top. I'll show a real example in a while. The best model of the Earth is globe. So if you take, for example, an orange is also a very good approximation of the Earth. It is not a sphere. It is not circular fully. What happens is, these are the poles. The poles go in. Okay. When the poles go in, it is squished on the top. Right. So it is not a full clean sphere like a full orange. If you have an orange, you have it as a full sphere. This is the different type of mandarin orange we call globally. So it has stouts on the top, right? So this is pushed down and then it is a sphere. So this spheroid, which is correct representation of the globe, is being done applied to all globes. So if you look at the globe here, on the top and bottom, it is slightly pushed. So if it doesn't push, it is a sphere. It's not a sphere, the real globe or real Earth, planet Earth, it is a spheroid. So slightly it is pushed down. So the best model of the Earth is globe, for which you can do mapping and other thing. And here also you can see the lat long lines. It has been dissected into latitude and longitude based on a particular coordinate system. So what is in the coordinate system is a set of the zero. Where is your zero? It defines your zero and the degree of separation between the lines. So coming back, we cannot use this. Why? Because you cannot carry the globe everywhere. Yes, this is the best model of the planet, but you cannot carry it everywhere. More, not good for making planimetric measurements, distance, area, angle, for example, because you have to zoom in. Zooming in and zooming out is not possible on a globe. So for that, we have maps. And when I say maps are a 2D surface. Again, think about it. We are thinking of a paper. 2D surface cannot be used for representing 3D unless and otherwise some limitations are addressed, right? So that part is what we will be looking at. So this is a 2D surface. You have a paper, right? And in this, you are going to represent the globe, which is 3D. So how do you do it? Is by projecting it on the 2D surface. So we look into some projections and the descriptions. As I said, the maps are flat. Maps are 2D surface, right? So map is a paper, and in that paper you want to bring all the information. When I say map, it's also the GIS map, because GIS is an electronic version of a map, a digital version of a map, right? So in this map, what do you see? You see the entire globe being focused into that area for that perimeter of your map. And you can see, as we discussed, the latitude is there and the longitude is there, right? So latitude is the top to down, longitude is this one. So you have your easting, northing, and the numbers are given here, right? So where you're looking at and how the intersection is where you have the lat long description. So moving on, why are these used? These are used because these are easy to carry, because you're going to use it for some analysis, some representation. You're not carrying the globe everywhere, right? So this paper map is easy to carry, good for measurements. I can show you that, for example, when you wanted to find the distance from between here and here, you can easily mark points and then estimate the distance. Yes, the Earth is not a straight line, but still you can see how the track goes or the trip grows in a map, and then you can estimate the distance. And then what else can you do? It is scalable. So what you see scale here represent like in a map. I've also discussed this when we did QGIS. It is how much of the map area is represented in the real life area. So for example, if you take one inch here, okay, let's say we're taking 1 inch here. So this 1 inch is equivalent to what 2000 or 20,000 in the real life scenario, right? So that is given by your scale, the ratio between your measurement on the map and how much of that is represented in the real life scenario is given as scale. Then we have scalable benefit of the map, because you can zoom in and zoom out. So I'll just say what is the scale in terms of usages is you can zoom in, zoom out. When you have a globe, you cannot zoom into a globe nor zoom out, because it is a ball which can be made for different respects. So if I want one globe, I can make for water bodies. If I want one globe, I can make for rural village map, but you cannot change it. You will have to make another one. So that is where a map is there. Even a map is stationary. You cannot change it. This paper map, what you see on the screen, you cannot change it. But the idea in GIS is you can import it. You can import it into the GIS software, and then you can make wonderful digital maps and data repositories for rural development. So how do you get from sphere to map? So the question should come. So this map is good. We all understand that the 2D map is better than the 3D version of the map. But how do you get from sphere or a spheroid to a map? That is what is called projections. Okay, map projections are used to project the data from a sphere onto planar surface. So projections are very, very important to understand, because we are converting a 3D image into a 2D image. We're converting a 3D real life figure into a 2D diagram. And for that, we need to make a lot of limitations and assumptions. And that is what projections does for us. We don't have to create new projections. We can, but I'm saying we don't have to, because QGIS have multiple projections. We will see why there is a need for multiple projections in this slide. See, imagine you have a paper, and in that paper you have drawn the grids, right? So the grids are already drawn. You have taken the lines as shown here. So you have lines in the paper, right? And you have vertical and horizontal lines. So now, if I put if it is circular, so now the globe is circular and like a spheroid, so it is circular, and on inside, imagine there is a light bulb. If you have a light bulb, you can see here inside the center, then the rays of the light bulb will come out of this paper, right? And let's say that it's a transparent kind of paper where it comes out. So when it comes out, each line is projected differently. So that is what you could see here. Even though the globe, you can see the globe doesn't want to have differences between the line spacing. We made sure that the line spacing is correct. But because of the projection and the angle of projection, in some parts, the light travels less distance, and so quickly it projects. Whereas in some parts of the globe, the light travels extra time, right? Because it's not a circle. If it's a circle, radius, all are same, but spheroid, right? So you have it going out. So you could see here, this line is traveling a longer distance, whereas this is traveling a shorter distance. With shorter distance, there's no distortion of the image, and you will have a better representation. So along the center, because you place the light in the center, along the center, the distance between the grids is same. However, if you go out of the center, you could see that the box gets elongated. And that is purely because of the light has to travel longer distance. It is an imaginary light is projected onto a developing surface, right? So this surface is an imaginary surface also, because it is a 2D image. It is a 2D screen where you are projecting your image. So as I said, you had let's say this is the sphere, and inside this you have a light bulb. and the light bulb is emitting. So when it emits, this is my surface, it hits. So how it hits, at what angles, is what defines a projection. And it also is important to note that the placement of the light bulb is very important to show where it is getting projected. So an imaginary light is projected onto a developable surface. Coordinate space becomes implicit. Okay, the space where it gets projection, it becomes implicit, and a variety of different projection models exist. Now you could see that if I'm working, let's say the globe is this, and this is the equator region. If I'm working in an Indian region, this image is fine. I'm putting the light bulb in the center, I'm getting good image. However, if my study area is Antarctic, Arctic, if I'm doing a flight calculation from India to US, so you'll have to cross the hemispheres, right? So for that, the center bulb is not just the perfect one. You have to compromise too much. So that is why there are multiple projections. Let me give you some example. And the surface also. The surface is not just a sphere and the light bulb. You could have multiple developable surface. So this is a conical projection surface where you put the light here and at a distance, not in the center, but at a distance from the sphere, and you let the light come as a cone. And when it comes as a cone, your certain parts are highly distorted in terms of elongation, whereas some parts are well represented. And that is because you have a notion to have more accuracy on the top, not on the sides. You don't care about I don't care about the side data. I'm not going to work on that part. I'm going to work mostly here. So this is the second cone, and within the cone there are multiple different types of cones. So just think about it. A projection can be in the center or outside of the center of the globe, and multiple locations it can be. And within that you have different shapes of how the light can come in. It is like imaginary. You put a light and you put a shade. So think about in houses they have night lamps. So depending on the shade is what they put on the night lamp, the light projects, right? So under the night lamp you can see light coming down. So if you make a smaller one, it focus. That is for reading and stuff. If you make a very spread one, it can spread a lot. So that is how you can make different projections using GIS. So three things we have seen. You need a center, which is the datum. You need the projection, which is where and how the 3D surface is projected on to the 2D surface. And we need a coordinate system. The coordinate system is how the globe is being cut in what degrees. So there are a lot of errors in this because you're converting from a 3D to a 2D surface. A single map frame should only have one projection. You cannot have multiple projections. But is this an issue? Yes, I'll show you why. Map projections always introduce errors and distortion. Always, it's underlined. Because you are converting a very complex 3D object into a 2D sphere, 2D space. So it is not going to be easy. However, we do the best. Why? Because this GIS software is usable for doing calculations, analysis, etc., whereas a 3D model cannot. Nowadays, computing can bring 3D image. However, the 3D image takes a long time to digest the information, right? So here what we're going to see is just a map. Okay, you don't have to if you look at the map, what you see here is what you see in the map is you have different projection and United States. There's a reason where you have why you have to have the America here, because we want to show that there is some issues in the projection. Okay, let me show you. So this is Alaska part. The Alaska part comes because Alaska is part of the United States. So US, if you know, is a big part of the US is in the Northern American continent. You have a big part, and then you have Canada, and then you have Alaska somewhere outside. So Alaska is also big. Okay. However, it is very, very towards the north. And the northern part, as I said, has a different projection. So in this, if you use a projection which is only suited for the central United States, then your Alaska is getting distorted. Let's say, for example, this is Alaska. It looks like Alaska in the same map, in the same projection, same map. Looks like Alaska is bigger than the part of the United States. Okay, so look at the states here. Some of the states within US is smaller than your Alaska, which is not true. Texas, for example, it's not as small or as big. So it's not definitely that small. So there is a distortion. It is a pull-push effort. So this Alaska has been pulled. So how should it be originally? Let's look at another projection which captures it in a different way. So this projection, if you look at, the image is not distorted. US is not pulled, and it is compromising some errors here, some errors here to have the best map. So this compromise is what is needed, right? So now if you look at Alaska, this is the state, and you have it as big as some of the states, but and also bigger than Texas. But more importantly, Canada can come here. You see the curve somewhere visually. If you look at, oh, the world is a curve, and with the curve, Alaska is drifting like this. It's if you roll it down on paper, it is 2D, but 3D is what the actual surface is, right? So you roll it on a sphere, and you can see that Alaska is kind of more curved because the curvature is high on the poles. So again, as I said, your poles have more curvature because it is pushed down. Here we have less curvature compared to the different locations. Okay, so the take-home message here is we are projecting data from a real world into a 2D space. And the 2D space is because your computer is a screen and the paper map is a screen, 2D surface. It's 2D, same as your screen. And with that, there is also need for doing some calculations and analysis, for which you need to define the center of your sphere and how it is being cut. Okay, how many small or how many big, depending on your need. And that is called coordinate system. Where you put the light bulb and showcase it on the screen is called the projection. And these two things, at least these two, not the datum, because datum is part of the coordinate reference system. These two things are very important to understand when you download data, because they would have downloaded, they would have set up the satellites for a particular data type. It is mostly in raster. And so when you download them, you should convert or reproject it into the other data frame. Okay, so let's say, for your example, your rainfall data from IMD is in XY coordinate system, but your satellite data on a digital elevation model is in AB coordinate system. So these don't talk to each other. So you need to convert. So you need to convert one projection into the other. Otherwise, there is distortion errors. Okay, so please read more on this. There's a lot of material on these things, whatever we discussed. This is just an intro I've given across this today's lecture. With this, I complete today's lecture. I will see you in the next lecture. Thank you.